So, welcome to the tutorial. I hope you can hear me. And I hope you found the videos on YouTube so that you have the theory. Today we will do the practical training with all of this stuff. And the idea is you also found the solutions for the tutorial. The idea for the future is that I'll do the solutions always live. And then I will prepare things in a recorded way so that I'll do a recording of this live tutorial. And then I hope that I can cut the final video from this tutorial out of the recorded stuff. So let's start. I will jump again to the screen. And I try to open the chat. So if you have questions or something like that, just let me know or send me a chat message. And then we can directly talk about things which you want to know. So the first question is, how many bytes are needed to represent the decimal number 1024? I will switch to a second camera so that you should see now where I can write. So if we have the number 1024, so we just have to think about these binary numbers. So this means we have 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and so on. If you write it in decimal number, we have 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. I directly selected this so that you don't have to think too much. You just have to fill these standard representation, and then you just do the following. The 1024 in decimal would be this number in binary. So, and then the question is, how many bytes are needed to represent the decimal number 1024? You remember 1 byte is 8 bits. Each of these numbers is 1 bit. So 1, 2, 3, 4, 5, 6, 7, 8. So this is the first bit. And to repeat, this is the least significant bit, and this is the most significant bit. I always write it in this direction so that the smallest number or the smallest value is on the right side. And then you can, here you have 3 bits filled. Then you have to fill it completely up to 8. So what you need is 2 bytes. Okay, so quite nice starting question. So let's go to question number 2. Question number 2 says, which decimal number is given by the binary representation 11010011 or 11010011? So it's also quite simple. You write the representation. So this means, so this was question number 1. Question number 2, we want to convert the 11001011 to a decimal number. So we do exactly the same here. So you can directly copy it. So here is 1, Here is 2. The 4 position, or the position with the value 4, is not filled. The position with the value 8 is also not filled. The position with the value 16 is filled. 32 is not filled. 64 is filled, and 128 is filled. So what you just have to do is you sum this stuff up. Plus, 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 plus. And the result, if you sum this up, is 211. So it's always the same stuff what we do. So this is question number 2. If you have question about that, just feel free to interrupt, okay? Let's go back. I hope you see this switching between the question sheet and the external monitor or external camera. So question number 3 is convert this number 111011101010101. So it's a nice number, you see, to an octal number. So question number 3. So I just note it down. 101, then 2 zeros, then 110, then 1011, 0111. So what you have here is you change to another system, so on the base 8. So what you can do is, of course, you can convert to the decimal system, and then you can convert to base 8, which is just dividing by 8. It's always the same style. So you can convert in like question number 2 to a decimal number, and then you take this and divide by 8, then you will get the octal number. But as octal, or also later on hexadecimal, has a connection or relationship to the binary system, so that you have a multiplier there, then you can use a trick. So for the octal system, you just have to combine always 3 elements. And then you have to just convert it to the decimal number, because for the octal system, the number representation, so the signs which you use are the same. So it's no difference. In the hexadecimal system, you need more signs, so more characters which you represent. Therefore, from 10 on, you have A, B, C, D, E, F. But in the octal system, you have directly exact the numbers which you have for the decimal system, and then you have to just change. So I write down again the representation. So this is 1, 2, 4, and for the next, we look onto this like it is a new representation. We have again 1, 2, 4, 1, 2, 4, and so on. And then we just convert. So this means we have 1 plus 4 is 5. Here we have just 4. If we have 1 plus 4 is 5. Here we have 2 plus 4, which is 6. The same again. And here we have, if we complete it, we have a 1. So this binary number is this number in octal system. So octal is not so common anymore in computer science. What you sometimes find is the hexadecimal system. Therefore, question number 4. Convert number from question 3 to a hexadecimal system. And this is the same style. So I would say you can directly guess how it works. So what you do is you just combine 4-bit blocks. So you make now your representation from here. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And then you look at each part like it would be a separate binary number. So you have the counting 1, 2, 4, 8. 1, 2, 4, 8. 1, 2, 4, 8. 1, 2, 4, 8. And then you sum up the positions which are filled with a 1. So in this case, we have the 1 and the 4 position. It's the same, must be the same like in the octal system, so 5. Then here we have the 2 and the 4 position, which is 6. Here we have the 1, the 4, and the 8 position, which is 13. So 8 plus 4 is 12, plus 1 is 13. And 13 is, I write it down, so 10, 11, 12, 13, 14, 15. This is A, B, C, D, E, F. So 13 is D. And here we have 2 plus 4 plus 8, which is 14. So and 14 is E. So this binary number is in hexadecimal number, this number. And this is the answer for question number 4. Any question up to now? If not, then we can continue with question number 5. So I'll switch back. Question number 5. Convert 2, 1, 2, 3, so 2123 to a hexadecimal number. So here you have again several possibilities. It depends up to you what you prefer. So I show you 2 samples. The first one is we want to represent 2123 in decimal to a hexadecimal number. So we can now do the same what we did between binary and decimal, or vice versa. So we can do a division by 16. So this means we take this number 2, 1, 2, 3 and divide by 16. It's an integer division, so we will have a rest, and this means in this case we will get 132 for the first division, and we will have a rest. So 11 numbers, or 11 does not fit into this division anymore. So we have the rest 11, which means if you remember, 11 was 10 is A, 11 is B. So we have B here. Then we take this and divide it further. So what we get is 8, and we have again a rest. So 4 does not fit into the integer number anymore. So this would be the fractional part here. Okay, so therefore we have 4. And then we take this again and divide it by 16. And then we get 0, because we have no complete 16 anymore, and therefore we have rest 8. So the result is 8. And then we read it in this direction. So this is the first number, second, third. So we have 8, 4, B in hex. Another possibility is that you take this number because dividing by 16 without a calculator is sometimes not so easy. So therefore you can do the normal thing, dividing by 2. And then you get this, for example, and then you take this 160 dividing by 2 is 530, and then take this 530 dividing by 2 is 265, rest 0, and so on, so that you will get a binary number which will look like this: 0, 1, 0, 0, 1, 0, and then 0, 0, 0, 1. And what you do is the same what we did in question 4. You build the same blocks of 4 elements and convert it back. So 1 plus 2 plus 8, 11. 1, 2, 4. 1, 2, 4, 8. And you have the same number with different solution ways. Okay? So let's go to question number 6. This time I will do it more or less in a prepared style. So for the next solutions, maybe we can do some small groups so that we have time to prepare things. So for next week, for example, especially for the programming stuff which you find there, maybe we can make small groups so that you have the chance to discuss things directly live online. But this time I just want to continue with this, let's say, sample, and then we can discuss if you have questions, okay? So let's go to question 6. Question 6 says, convert the number 17253 in octal to a hexadecimal number. So in this case, we have to use the trick to jump to a position which is represented in binary, because then it's easier. So what we do is we write down the octal number, and then we convert this octal number to a binary number. So if you remember, we made some small sections of 3 bits. So therefore, we just have to do a conversion here to a binary number. We just look onto each number, and then we see this is 1, 1, 0. So 1 plus 2, 4 is not filled. In this case, we have 5. So this means we have a 4 and we have a 1. In this case, we have a 2. This means this. And here we have a 7. So we need the 4, the 2, and the 1. And in this case, we have a 1. Therefore, we have this situation. And if we have this situation, we then just combine blocks of 4. And write down the representation again. So in this case, you remember 1 plus 2 plus 8, which is B. This case is A, it's 10. This is E, and this is 1. So the hexadecimal representation is this from the octal. This is question number 6. Okay. Question number 7. So we can go quite fast through this. It's always just playing a little bit with numbers. So later on in the next tutorials, you have to do some programming, and therefore you'll see it's a little bit more, let's say, sophisticated, or a little bit more work. Question number 7. So question number 7, which decimal number is given with 487 hex? It's the same style what you already know. So we note down 487 hex. So do you remember? Of course. So you have now base 16. So it's 16 to the power of 0. Then you have 16 to the power of 1. And you have 16 to the power of 2. So what you calculate is 4 times 16 to the power of 2 plus 8 times 16 to the power of 1 plus 7 times 16 to the power of 0. And if you hack this in your calculator, then you will find out that it is 1159 in decimal. So, okay, this is just playing with these numbers so that you get a feeling of these different positional systems. Where we need it, or where it is used, is for binary numbers. So therefore for binary formats or something like that. And therefore you should know what the differences are between integers, unsigned integers. So if you remember from the lesson, you will see that there are a lot of possibilities of types. And these data types are often a cause for really strange errors. So if you do programming, and therefore this playing with these numbers should just give you a feeling of where are the limits. So how can we deal with these limits? So it's also a feeling that you see that, for example, if you buy memory, or if you if you discuss something about computers, you will always have this factor of 2. So if you have a mobile phone with 8 gig memory, then the next one is 16, and the next one is 32, and the next one is 64. So it comes exactly from this system. So therefore, you should just get a feeling of that. Okay, so in the next question, question number 8, deals with this. Because in the most programming languages, also MATLAB has this, you have data types. So MATLAB, everything converts to double. So you, in a first attempt, you don't have to think about this stuff. But if you look closer to this, and if you want to read binary formats, then you have to deal with this. And therefore, you have to know things like that. So where are the limits? So you find in the lesson that one very famous error in history brought the Ariane 5 rocket to a crash. So it was exactly this. They used a short and should have used an integer, because they used code from the Ariane 4, and the acceleration numbers were different. So a large rocket has larger, let's say, accelerations or numbers in these changes, and therefore they tested everything, and they had everything working in their test system, but the problem was that the reality was different, and therefore it's always dealing with these limits of the numbers. So question 8 wants to know what are the limits for unsigned int and for int. So if you use MATLAB, it's quite simple. You just enter max int or min int and things like that. So I want to just to show you how it works. So if we have 8 bits, to start with 8 bits, so if we want to set the limit for that, we have to fill all 8 bits with ones. So we have 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128. So this is the maximum number is then 255. So you get the same number if you set the next one minus 1. So this value minus 1 is a complete fill value, because if you have this number plus 1, you will get this set up. So you need 1 byte more and you will have this set up. So this minus 1 is this plus 1 is this. And therefore you can calculate the maximum if you take the next value. So let's do it with the red here. If you take the next value, which is 256, and you subtract 1. So it's, for example, 1, 2, 3, 4, 5, 6, 7, 8. So this is the power of 0, 1, 2, 3, 4, 5, 6, 7, 8. So you have 2 to the power of 8 minus 1, which is also 255. So therefore you can calculate the maximum of representable decimal numbers. For example, if you have an integer, and this is was also one question which I got as a feedback to the lesson. How do you know, or how does the computer know when or when it should use the two's complement? It's exactly given because of the type. So if you have an integer or int means you have the plus and the minus range, so it's a signed type. If you have an unsigned integer, then you have just the plus type, because it's not signed, and therefore you can use the complete integer value. So in this case, it's quite simple. You can calculate the maximum number if you have 2 to the power and integer are 4 bytes. So all integers are 4 bytes. And therefore, if you have 4 bytes, you can use, with 4 bytes, you have 32 bits. So you have 2 to the power of 32 minus 1 is the maximum number. In written form, it's this. Okay, so this is the maximum number, and the minimum number is in this case 0. You can use all 32 bits without any respect to plus minus bit. So in signed int, so in this case int, in MATLAB, for example, you also write the number of bits to it, so it's a little bit more clear. You don't have to have this in mind. So in MATLAB, the type is like this int32 or uint32 for unsigned. In this case, you lose 1 bit. You lose 1 bit because of the sign. And in this case, to come back to this question about the two's complement, if you have this case, automatically the two's complement is used because it's a signed representation. In this case, the two's complement must not be used. You just have the positive range. And the use of the two's complement is nothing more than shifting the negative part to the positive range. Okay, so therefore it's quite simple. And therefore we have the maximum number is 2 to the power of 31 minus 1. This is the maximum. Then we have 0, and the minimum range is 2 to the power of 31 minus 1. So it's the same, but we lose, or we have 1 number more in the minus range because we do not have to represent the 0. This is because we have no minus 0, and therefore we have 1 number more. In this case, we can subtract one more, and therefore you have to the plus range, you have from the absolute value, you have 1 less and to the minus range, you have 1 more in the absolute range. Okay. So for this is the minimum value. Maybe it would have been better if we did arrange it in the vice versa version, so that the maximum is on the right side, and this is the maximum version. Okay. And with this, you can calculate all of these maxima, minima things. And this is really relevant because if you look to this again, if you have this number and you add 1, you will come to this position. And if the type just represents, for example, 8 bits, then it will jump over to 0. So for example, for the Ariane 5 rocket, if you have an unsigned integer or unsigned short and the number is bigger, then it jumps to a value which fits again. But you would have needed much more here in the higher ranges of bits. And this can cause real dramatic problems because you use the wrong number and you have this limited world of your computer. And with this, the next question deals, because there is one very famous problem. So it's also similar to the year 2000 bug, where a lot of things were expected and where they had to prepare the processors. The next critical situation, and you have it everywhere in all of the calculations where you use time, is the situation where you use the Unix time or the computer time. Because the Unix time or computer time is called the epoch. Also in Windows systems or in Mac systems is the same. And it's defined as the epoch because it's the starting time from the 1st of January 1970, 0 o'clock, 0 minutes, 0 seconds. And then you have a counter, and you have also a battery in your computer. So if you switch it off, the battery keeps this counter available. So it's a hardware clock, and the hardware clock feeds the software clock in your operating system. And everything starts from this date on and counts seconds. So if you use now different data types, then you will come to a situation that your maximum day or date which you can represent will be somewhere in the future. And if you really calculate on that, then you will see it's not so far in the future. So therefore, question number 9 deals with this. So Unix systems define the epoch as starting time of their time counter on what I said, 1st of January 1917, 00000. The counter counts seconds beginning on this start date. The internal type is in most programming languages called time underline t or underscore t, and is defined during different define mechanisms, in most cases to long int. So long int means it's a signed integer, and on a normal computer which has no 64-bit system, so if you do not use the Windows 10, for example, or if you do not use a modern Linux, then you will run into this problem. So on all 32-bit systems, the date comes to a problem which is similar to this millennium bug, because you have just 32 bits, and as it is a signed integer, it's also the problem that you will run into this because you have just 31 bits available. So what would happen if we change the type to unsigned long int? So first of all, when is this millennium bug? It's not a millennium bug, but it's a counter bug. And what would change or what would happen if you change it to an unsigned? And why is this problem automatically, with quotes, solved on a 64-bit system? So with 64-bit system, you will have the same problem, but it will come really, really late. The problem is that with a 64-bit system, or this date is, you have to calculate manually, because the normal computer does use the Unix time, so you cannot calculate it with Excel. But I can show you how the calculation works with Excel. So if I open it, just focus on the top here. So because this is the solution for the for one of the next questions, the Hornet scheme. So if we use int, we have this maximum number, 2 to the power of 32 minus 1. And then we'll have this number. And then if you sum up, add to this time of seconds, then it will happen on the 19th of January 2038 at 3 o'clock 14 minutes 6 seconds that you will jump back. So at this date, the next plus 1 second will have this date again. So on this day, at this time, we'll jump back to the starting point of all computers. So, and if we change it to unsigned int, we have from 0 to this, so we have the double range. So, and then we will reach this date. So we will end in 2106. So we have about 70 years more time to fix this bug in a 64-bit system. So it will be much better, much better. So it will not arise anymore in our humans' lifetimes, and therefore it's automatically solved. As I said, if you have questions, just interrupt, or if you want to repeat things again, just let me know. So another situation where you find these hexadecimal numbers is with colors. So and therefore we start with question number 10. Question number 10 is about the colors, and for the colors we have the red, green, blue mechanisms. There is a different one which you also will find, which is for the printers. So there is a conversion between this and printer-based system, but we focus onto the red, green, blue, which is for monitors. So, and then the question is, how many colors can we represent if each color, so in red, in green, in blue, so each of these red, green, and blue is represented with 1 byte. And if the number, so the height of the number represents the intensity of this basic color, so of the basic color red, of the basic color green, of the basic color blue. So what we have then is we have 3 bytes. So let's jump to my external camera. So we have 3 bytes. And if you remember what we can represent with 1 byte, we can represent the range from 0 to 255. So we have at least 256 different possibilities. This means we have 256 possibilities for red, for green, for green, and for blue. So what we get as a final possibility range is if we multiply all of that, and then you will see that we can represent 16 million of colors. So these are all of the possibilities which we have. And if you compare this to the human possibilities of detecting colors in your A's, then you will see that these are much more colors than what you can really detect with your A. And therefore, for a monitor, this is enough. This is called true color representation, and therefore it's enough. If you want more brightness or things like that, then you can increase this number. But for the standard things, it's more than enough. So all of the monitors deal with this red, green, blue. And therefore, if you program internet web pages, you will come to the next question. If you want to represent your colors on internet pages, so here is a simple internet web code, HTML. We'll hear about HTML later in this semester, where you will see this markup language, HTML and also XML. And for now, you just have to know that you have a channel format starting with HTML. Then you have a head description where a lot of things like meta information is stored. And then you have the body, which is the real web page. And then I prepare a headline here. So, and you don't have to think about this. It's just a definition for the font, and it will print hello world. So in this case, we'll represent hello world. And here the style is defined as color, and here you see the hex code. There are two possibilities. You can write RGB, parentheses open, and then you can directly use a list separated with comma with decimal numbers of the colors. Here you can represent the hexadecimal numbers. And the first two, remember, 8 bits. If you want to represent it with hexadecimal, you make blocks of 4. So always 4 bits are one of these hexadecimal symbols. So the first 2 are 8 bits, the next 2 are the next 8 bits, and the next 2 are the next 8 bits. So what you see is red, green, blue, and therefore you can change the color here. In my case, I can open it with a browser, and then it looks like this at the moment. So this is this hello world symbol. I already entered the solution. Therefore, what you should do is you can go into this web page, and then you have these sliders here, and then you can change the color which you want to use. For example, this orange. Let's go to this orange. Okay. And then these are the decimal numbers for the color. So for red, green, blue, representing this color. And then you convert it to hexadecimal. So you can do what we did manually. I don't want to waste time, so I use a calculator in this case. There's a question, can you upload the Excel sheet for this tutorial? Sure. I can do this, of course. And then we enter just, so we have 184, and then you directly see here the hexadecimal representation, which is in this case B8. And then we enter, we clean things, and then we enter 78, and you have the hexadecimal representation for the next channel. And then we enter 13, and you have the hexadecimal representation, which is 0D. So you always fill up on the left with zeros. And if we open the editor with a code, then you can change this number character here. This sign here just says that it's a hexadecimal representation. And if we enter now B8 for E0D, and if we save it, and if we open this again and reload it, then you will see it's this color, okay? So the other version would be if you directly want to use the decimal numbers, because it's always difficult to convert, so, or it's not so nice that you have to do the conversion. So you can also write here, instead of this number character, you can write RGB, and then you make 148, 184, 78, and 13. And if you store this, you have the same color. Okay. But you should see that the hexadecimal numbers have some practical use, especially if you have your web pages, your styles, then you use these things and you have to deal with these 8-bit representations. So therefore, it's a nice application for our binary and numerical stuff. So any other things? As I said, just if you have questions, just enter some comments to the chat or things like that, or interrupt me in person. So I will cut out of the final recording your voice and your face, so that it is not published. This is the idea. So you can ask, okay? I think others would also have maybe questions. So let's come to question number 12. Question number 12 now deals with the same stuff like question number 11. Now we just want to use the red, green, blue colors in MATLAB. The only difference is that in MATLAB you have to represent all of these numbers with floating point numbers. So let's read question number 12. MATLAB also offers individual colors based on red, green, blue ranges. Draw a circle and paint it with the same color like in question 11. Take care that MATLAB works with floating point red, green, blue. Let's switch off MATLAB. So in MATLAB you can draw the circle using the function rectangle, for example. So I will do this, rectangle, and then I give a position. In my case, I want to, position with uppercase P. In my case, I want it on 2, 4, 2, 2. Then I define that the curvature should be 1, 1. So it's a circle definition, and then I do what the question asks for, face color. And here I define a vector with these 3 elements, the 3 elements for red, green, and blue. So the first one is 0, 0, 0. If I do this, I will get a circle. So if I want to change it, I can make axis equal, so that I have really a rectangle, so really a circle. And then you see 0, 0, 0 is black, for example. The maximum number is 1.0, 1.0, 1.0. So to show this again, it's white. So 0, 0, 0 means black, 1, 1, 1 means white. So and we have now a predefined color which we want to use, and therefore we have the maximum number is 1, the minimum number is 0, and therefore if we want to paint exactly this color, we say 184 divided by 255, because this is the maximum number which we can represent. And this is the difference to what I had in my previous tutorial. So here is the correction. So we say, let's take again 184 divided by 255, and the next one is 78 divided by 255, and the next one is 13 divided by 255. And if we plot this, then you will see that we have exactly the same color like here. So you see that these color codes are quite important if you do your own style sheets, your own programming of color maps. MATLAB offers you a lot of possibilities for colors, check colors and whatever. So if you want to prepare your own color maps, then you have to know these binary numeric numbers. Let's go to question number 13. So what you have to think about is that if you enter some numbers on your keyboard, you do not really enter the number, you enter some characters. You will see in the text and binary, though it's the lesson from today, I guess. So I produced a few videos ahead, so I don't know at the moment which lesson is currently the up-to-date one. That we have the character which must be converted to the representation in the ASCII table, and then the ASCII table must be converted into a calculatable number, and vice versa. So the computer must do this work for you, and this question number 13 deals with this. The Horner scheme method is the way if you have a number available in your computer and you want to convert it back to a decimal number, and then you use this decimal number to convert it to with the ASCII table to the character. So you have to do a lot of calculation. You do exactly this what we did manually. So you check which bit is set, and then you convert everything. And in most cases, you can simplify this calculation if you use this Hornet scheme. Because what is done here, the Hornet method is used to reduce the number of operations for a conversion of binary numbers to decimal numbers, using the principle of factoring out in a polynomial function. So what you do is, here is a sample. You have a2 times x to the power of 2 plus a1 times x plus a0. So what you can write is, you have a2 times x, and then you can factor out or multiply out the x for the first two terms. So you have at least a 2 times x plus a 1 in parentheses times x plus a 0. So what does it help? It means you have, if you look onto the beginning questions here, if you look to this, you have 1, 2, 3, 4, 5 different operators. So multiplications are more cost intensive than additions, but if you just count the number of operators, then we have 5 here, and if you compare it to here, we have 1, 2, 3, 4. So we reduced this by one operation, and therefore, for example, if you use this binary number, so how would the Horner term look for binary number 1010111111? And how many calculations are saved with this method? It looks quite different. And if you have a 32-bit integer, it's much more than this. And therefore, I jump back to the Excel, and we look onto this here. So I just noted down what we have. So here is the representation. This is the power of, so 2 to the power of 0, of 1, of 2, of 3, of 4, of 5, of 6, of 7. And in this case, we have 1, 2, 4, 8, 16, 32, 64, 128 as representations for these places. And now we write down the number which we had. So if we go back to here, we have 1, 1, 1, 1, 0, 1, 0, 1. So we have 1, 1, 1, 1, 0, 1, 0, 1. This is our binary number. And if we calculate, we just have to multiply this times this and sum up. So the decimal number what we have is this. So we have 1 times 1, 1 times 2, 1 times 4, 1 times 8, 1 times 32, 1 times 128. So we have 175. So this means in a first attempt we have this situation: 1 times 2 to the power of 7 plus 0 times 2 to the power of 6, and so on. I also take into account this 0 because then we can evaluate the complete Horner scheme, so that you will see the complete reduction. So in this case, if you write it in full operation mode, then you have 35 different operators. And I said multiplications are more cost intensive than an addition. So even if you would take into account this, then it would be much more difficult or much more cost intensive. But if you just count the operations or operators, then we would have 35. If you do the first factoring out, so if you multiply out this 2 here, then we have 1 multiplication less here, less here, less here, and so on. So with the first Horner attempt, so just multiplying the first out, so this is the 1 times 2, and then we have this parenthesis, we'll reduce it to 29. And if we continue to this, so the next we look into this and multiply out or factor out this, then we have this, and so on, and we do it up to the end, then we would have 14 operations instead of 35. So is less than half of the number of operations. And therefore, it's a quite nice method to convert from the binary number to a decimal number. And this method is also used in computers to show you the decimal representations. What I did not mention, for example, in the class is that meanwhile you have also binary codes. You'll see it maybe in one of the later lessons that you have also data types which represent binary numbers, but then you have at least you have always these conversion things behind. Okay. So I think you got the idea behind, and therefore you have the same number. So and you reduce it tremendously. Okay. And final question. Almost 1 hour is over. So final question is question number 14. Convert the C program. By the way, you see already the program in the lesson because I used it as a sample for this stuff. So in principle, it would just be necessary to type it from the lesson. The idea is that you should also write your own program to see that this problem of integer and iterative processes is still available. It's not because of the fact that you use MATLAB and you have double precision that the problem is solved. So if you do iterative processes, if you want to calculate, for example, a few days ago I heard about that an asteroid change its orbit and might come back in 30 years and might come closer to the Earth, not the next 2 periods, but for example, the 3rd period then. So if you do these iterative processes and if you lose because of your floating point arithmetic accuracy or precision, then you will have to deal with huge effects. And therefore, you should play with this MATLAB again so that you see that the problems are still available. So the idea is convert the C program, which you find in the slides, using 3 different representations of the Verhulst equation to the MATLAB program or MATLAB language, and plot the results to show that the chaotic situation or this deterministic chaotic situation is not a language dependent thing, but is a general problem of floating point representations. So what we do is we open MATLAB and then I just show you the prepared thing. So we go step by step through this program. So what I always do at the beginning is this clear all, close all, and CLC, which just cleans up things. And then I define 3 equations. I want to do a calculation of 100 steps. So if you do this preparation, you don't have to always change the matrix. So if you create a matrix and you always resize it, it's a new allocation of memory, and this costs a lot of time. So you should keep this in mind if you write MATLAB programs. If you already know how much space you need, it's much better if you prepare everything at the beginning. So I want to calculate 100 steps with these 3 different calculations. I start with the start value 0.01 in all of the calculations. And the difference is, so it's just different calculations which you find also in the slides. So for example, the difference to here. So this is just a multiplication in. So I multiplied in here the factor. And in this case, it's just I replace the power of 2 with a multiplication. So that I multiply these 2 values instead of taking power of 2. So, and if you calculate this, I do this iteratively, 100 steps, and I just fill in according to the iteration position. I fill in, so I start with the first iteration position is 0.01, and the next one is on position 2. So iterator is 2 in the next calculation, and I use the previous one to calculate the next one. I always calculate all of the 3 results, and I iterate to the next step. And if you run this, so it will do a calculation, and then you will see this plot. And it will show that, for example, if you zoom in here, you will see that there are slight differences. So, and that there is a situation, for example, if you compare the red with the blue one, that in this case you have a almost died out petri dish. If you want to watch it in population of something in a petri dish, for example, or population of human people, human beings, and you see it's almost died out in this calculation, and it's very overcrowded in this calculation. So if you zoom out again, if you compare the first part here, you will see that it fits quite nicely here. So there are not so many changes, and at one point this calculation starts, because then the surrounding errors happen, and then you have this problem. Okay, and it's with all of the computer languages, you know. So therefore, numerics is a very essential part if you want to deal with calculation, because numerics is the mathematic which deals with a limited world of a computer. And the limited world is given by the representation of data types or of numbers. So that's it. So it's more or less a frontal tutorial. As I said, I want to test next week a little bit of group work. But first of all, you should have all of the things here available. I won't give you a solution sheet because you have everything during the tutorial, and you also have the film. Therefore, you can have a look at it. What I will do is maybe this Excel sheet I can upload so that you have it available, so that you can play a little bit. So that's it. That's the whole tutorial. So 1 week without me. Enjoy the time. See you next week and have fun. Bye bye.